Welcome back, Hononegah Geometry. Today we're going to talk about 4.4, congruence and transformations. We're basically going to be moving multiple transformations, moving things around and talking about how they are still congruent to each other because they are a rigid motion. But we'll get into that in just a little bit. Name the vector and write its component. So it's vector CD, and its component from C to D is down 3, so that's a -3, and to the right 7. So we have a component form of -3, 7. Find the distance from A to B. So now, distance formula. So this is a review type question. Distance formula is x minus x squared plus y minus y squared. So I end up with 9 plus 16 squared. Add those two together. I get square root of 265, which is approximately 16.3. All right, let's get into today's topic now. Congruence and transformations. Understanding and identify congruent figures, describing congruent transformations, and then using transformations to solve different problems. Here we go. Two geometric figures are congruent figures if and only if there's a rigid motion or a composition of rigid motions that maps one of the figures onto the other. The figures have to have the same size and shape. To me, that's the biggest thing that we have to worry about. If I move something around, whether I do a reflection, whether I do a translation, whether I do a rotation, it's still keeping the same size and shape. If you end up stretching something, okay, making it bigger, again, we'll talk about the dilations and things like that later, and that is not congruent. Now I've changed the actual shape. You can identify congruent figures by identifying a rigid motion or a composition that maps one of the figures onto the other. This is all 4-1 to 4-3. Translations, reflections, rotations, and any composition of those. So here we go. Identify figures in the coordinate plane and explain. Now, the explanation is basically that they did not change size and shape. And you can actually explain what happened to each one. So like y is quadrilateral. C, or I should go A, B, C, D, congruent to triangle or quadrilateral. Q, I'm having a little issue here. There we go. N, P, Q, and R. And so when you're looking at that, you're basically describing how many units it went 2 units left and 6 units down, which then makes it congruent. So 2 units left and 6 units down. Next one, I have triangle IHJ is congruent to triangle. It's probably the best way for me to describe it. All the way down there at the bottom, TSU. And so what happened between those two triangles? Well, you got a rotation of 180 degrees. And the last one, we have triangle EFG is congruent to triangle KLM, and that one's a reflection on the x-axis. So that's the explanation that they're looking for. It does not change size or shape, and I apologize for my handwriting here. I'm just going to rewrite it here to make it just a little bit nicer. So I'm just going to write quadrilateral A, B, C, D is congruent to quadrilateral N, P, Q, and R. Another name of rigid motion or a combination of rigid motion is called congruence transformations. Because the pre-image and the image are congruent, the terms rigid motion or congruence transformation are interchangeable. I like to refer to it as a rigid motion. I think it's the easiest way to understand it. It also can be called a symmetry, but a rigid motion to me means I did something, but I didn't change the shape. Describe the congruent motion that maps ABCD to EF. Now, looking at this, you have to understand which one goes with which. So A goes with E. So this is not a rotation. Okay, a rotation, it would end up A would turn over here. And so that's not true. And so it's not a rotation. But what I can do is two different transformations here. I can flip it over here. I can reflect it across the x-axis. So there's A. So there's a reflection on the y-axis. So that moves it to the other side. And then I can do just a translation down. So there's B. Here's C, and here's D. So that would be my first. And then when I just move it down, I would do a translation down 4. Now, if you wanted to describe it this way as a rule, you would say x and then y minus 4. If you want to describe it as component form, you'd have 0, negative 4. So again, describing your congruence, or describing what's happening when I get from the beginning, the pre-image, to the image. Describe the transformation. And again, it's important to understand J goes with P. And so notice how far it is from the origin and how far it is from the origin. That's a description of a rotation. So a rotation, 180 degrees. Composition of two reflections result in either a translation or a rotation. So I do two reflections. I'm either going to get a translation or I'm going to get a reflection. The composition of two reflections in parallel lines results in a translation described in a theorem. Now, if lines K and M are parallel, then the reflection of K followed by the reflection of M is the same as a translation. So if I have two parallel lines, that's an if. If I have two parallel lines and I reflect on one line and then reflect on the other, ultimately this is just a translation going from B to B double prime. So from here to here is just a translation because I reflected it across two parallel lines. Now this next one, I'm going to explain it, but this next one ultimately, if I go from one point, okay, to the other one on the bottom here, it's technically 2D, and I'll explain why that would be in just a little bit. So here we go. In the diagram, the reflection across line K maps GH to G prime, H prime, and a reflection on M goes from G prime, H prime to G double prime, H double prime. You're also told that HB is 9, and you're told that H prime to D is 4. Name any segments that are congruent to each. So GH, well, GH would be congruent to G prime, H prime, and would also be congruent to G double prime and H double prime. HB, so looking at the picture, H to B would be the same as H prime to B. GA would equal A to G prime. Now, does AC equal BD? And the answer to that question is yes. Here's the reason. We have parallel lines, which then create a rectangle, because we have 90-degree angles. And so yes, the distance up here and the distance down here would be the same. So it would be 13. Now, what is the length of G? to G double prime. Using the formula, the answer is 26. It's 2 times D, but I want to explain it in a little bit better way. The figure created, and we haven't talked about parallelograms yet, but the figure created here is a parallelogram. And so the distance across the top would equal the distance across the bottom, just like a rectangle. And so 9 plus 9 plus 4 plus 4 would be 26. So again, there is a formula involved there, but ultimately to me, it makes more sense to think of it as a parallelogram that ultimately has congruent sides on the top and congruent side on the bottom. Composition of two reflections with intersecting lines is a rotation, as described. The angle measure here, if I do a double reflection, so I reflect it across K, and then I reflect it across M, the angle measure created by the two reflecting lines, this arc would be double. So looking at this picture, I have fish that I've reflected across K and then reflected across M. If this angle measure is 70, what is the angle measure from F to F double prime? The angle measure would be 140 degrees. It would be double the angle measure between the two reflecting lines. And so next, in the diagram, the pre-image is reflected across K and then reflected across M. Describe the single transformation. This would be a reflection. I apologize. This would be a rotation. Not sure why I said reflection. Rotation of 160 degrees. And if you want to say counterclockwise, that would be more specific. Now, if you did a rotation of 76 degrees and instead did two reflections, what would the measure of the angle form? So again, if I wanted to go 76 degrees, they want to know what this angle would be then if you use two reflecting lines, and the answer is 38 degrees. This is a very difficult SAT question. In order to add and subtract fractions, you need a common denominator. Now, there's a couple different ways of looking at it, and I'm looking at what they did, and they ultimately had to get a common denominator. So you need to factor this one. And so I'm going to take out an x and a y, and I'm going to get x minus 8. And so then what does this one need in order to have the same denominator? Well, it would need to multiply by x and y to the top. And so now, using a common denominator, I have xy, x minus 8, and xy, x minus 8. And the top, I'd have xy squared plus 12xy. And over here, I'd have xy minus 8y. And so now, combining these two, I'd have xy, x minus 8, over, adding like terms, xy squared plus 13xy minus 8y. And if I distributed this back in, it would end up being C is the correct answer. All right, your homework assignment is a worksheet, section 4.4. If you have any questions, please make sure you talk to your teacher. There's a good joke here about math if you want to look at that. And good luck.